So here we have a beautiful test. Calc 1, locally Math 1650, third exam. Starting to get into those applications of integration and integration. What a lovely topic. And this was fall 2024. Excellent vintage. I was teaching the class that semester, so I wonder, will we get to see my problem? Well, I suspect we'll know when we come across it. So we have our multiple choice 6 problems and 4 workouts. Plenty for us to do, and we should just jump into it. But of course, as always, remember to put your name down, because if you don't put your name down, we can't give you the credit. And you deserve that credit. Let's go for it. Multiple choice. Now remember, we don't have to show our work. So if we have a way to get the answer without going through the whole process, great. Of course, we can do the process. We just need to make sure we get the right answer. All right. Number 1. Apply Newton's method to estimate a root of the function x cubed minus 5x plus 1. And we're told, hey, we have an initial guess. What's the next guess? So remember, Newton's method says what? It says, hey, we're trying to find a root. So in other words, we're trying to find this. That's a root. Where we cross, and we say, well, hey, I have a guess. It's probably wrong. Most guesses are. That's why they're called guesses. They're not called know-its. But then we say, well, let's use the tangent line to make the next guess. Now, all that is to say, that's what's going on under the hood. But the nice thing is there's a nice recurrence. It says the following. xn plus 1. So your next guess is take your current guess and do a correction. You subtract, fxn divided by f prime xn. So, we have f of x. All right, what do we need? We need f prime. So we're going to find f prime. No worries about that. Take a derivative, f prime of x, 3x squared minus 5. So, our next guess, right, because we have a guess, we want the next guess, x1 is x0 minus f of x0 over f prime of x0. Okay, so plug in x0. Don't forget to put that in. I've done that before. I've always felt bad when I do that. F of x0. Okay, plug in 1 into the function. And 1 is easy. You just coefficients, right? 1 minus 5 plus 1. And that's negative 3. Okay, right? 1 minus 5 plus 1. Now, plug in 1 to derivative. 3 minus 5. Negative 2. Okay, so what do we have? Well, the negatives cancel. So it's 1 minus 3 halves. Well, that's 2 halves minus 3 halves, which is negative 1 half. And that's an option. Now, I should say, be a little bit not super enthusiastic because they know your mistakes. They know the kind of mistakes people make. So pay attention and be careful. Just because your answer is there doesn't mean you didn't make a mistake. But if you were careful and methodical, you should be good. And if in doubt, we can always go back when we have time. Number 2, use a midpoint Riemann sum with 3 equal subintervals to estimate this integral. All right. Well, what can we do? What's going on? Now we're going from 0 to 6. And it says we have 3 subintervals. So that says we're splitting this up into 3 pieces. They're equal. Well, it turns out it's easier to break 0 to 6 into 3 parts. Each part will have length 2. So we have 0, 2, 4, 6. Now, above this, we have a function. So there is some function. All right. That's obviously not what the function looks like, but let's pretend like I could draw. And what can we say? Well, we're after the area. And the way we'll do it is the idea of Riemann sums is to say, what if everything were rectangles? So rectangles, that's not so hard. We have the widths are 2. Got to keep our widths about us. What are the heights? Well, for the heights, you have to say, where do you look? And this is where that midpoint comes in. So we take the midpoint of each part, 1, 3, 5, plug it into your function, and that will be your height. And there you go. So what do we do? Well, in our case, we say, think of this as our f of x. What we'll have is that the first rectangle will have area 2 width times height, f of 1. The second rectangle will have width 2, height, f of 3. Third rectangle, this last one, what will that have? Well, it'll have width 2, height, f of 5. And when I say f, plug it in. Okay, so 1 minus 3 is negative 2. 9 minus 9 is 0. Oh, that's very convenient. Nice. Zeros are nice. We like zeros. 5. 25 minus 15. Okay, that's 10. Okay. So what do we have? We have minus 4 plus 0 plus 20 is 16. And there we go. 16 is an answer. Now, by the way, there is something I want to point out. They put in a little like, oh, are you paying attention kind of answer. A lot of people forget the widths. And so in other words, they'd say, oh, it's the value at 1, value at 3, value at 5. And if you put those all together, you would have gone 8, which is an option. See, that's what I mean when they say they know the common mistakes. So be careful. Don't rush yourself. Just remember, if you see Riemann sum, say, you got a bunch of rectangles. Life is good. Now, on a side note, if you didn't know what else to do, you could try to integrate this and say, well, what does this integrate to? And see, is it something close? But the problem is that there's a couple answers that are close together to the right one, so it might not be enough. If the answers had been spaced out far enough, it may have worked, but all right, come on, move on. Number 3, compute the sum 0 to 8, 2n plus 5. If needed, you may use the formulas. So they give us formulas. Ha, that was nice. Now, there's a couple of ways to do this one. One is we can use the formulas. And by the way, you might be saying, what are they testing us on? Well, what they're testing us on here is working with that sum notation. So this Greek letter sigma for sum, S for sum. So can we do a sum? Well, yeah, we can do something, right? All right, I'll be here all day, right? Okay, so we have the sum 0 to 8 of 2n plus 5. Now, the thing is, we can break up over this plus. And the other thing is we have the 2 and the 5. And those we can pull out. So this is the same as 2 sum from 0 to 8 n plus 5 sum 0 to 8 of 1. Now, let's do these two one at a time. So what do we have? Well, here, it's like we're adding n. See how we have n? That's pretty good. Now, how do we do that? Well, we say we're starting at 0. This one starts at 1. But notice, if you start at 0, you get 0, right, when you put 0 in. So this really doesn't matter if you start at 1 or 0. I can put a 0 there if it makes us feel better. So I say, hey, let's use our nifty formula, right? So that says we're going to 8. So 8 is our value for k. So this is 8 times 8 plus 1 is 9. Divide by 2. Well, we have a 2 in front. And so put that together. It's 8 times 9. 72. Okay, great. Now, what's this? Well, we're not adding n. We're not adding n squared. What are we adding? Well, we're adding a 1 and 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 a 1. How many times? Well, 0, 1, 2, 3, 4, 5, 6, 7, 8. Now be careful. That doesn't mean there are 8 ones. How many ones are there? 9. Because we started at 0, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So this sum is 9. So we say, aha, so this is really 5 times 9, which is 45. So now we need to add the two together. Well, notice in the ones, we have a 7, and actually that's enough to tell us the answer is E. But you also add the first leading digits, you get 11, which means it should be 117. So there's our answer, 117. Now, I mentioned you can do this other ways. This one, if you look at it, we have 9 terms. And here's a fun fact. These are growing linearly, which means that you keep adding the same amount each time. So it starts as 5, and then 7, and then 9, and then it keeps going all the way up to the last number. 2 times 8 is 16 plus 5 is 21. Now, here's the fun trick. If you add the ends together and divide by 2, well, 21 plus 5 is 26, divided by 2 is 13. That says, on average, the values are 13. So if we added them all up and divide, well, but how many numbers are there? There's 9 numbers. So what is 13 times 9? It's 117. Now, if what I just said didn't make any sense, don't worry. You don't have to know every way to solve a problem. That's the fun thing about math. You just have to know a way. Now, it gets a little bit more interesting when you have many ways. So that's okay if you're like, what happened? So what I was just saying is, if you add the first and last, divide by 2, and then multiply by how many terms you add, that'll get you the right answer. But however you get there, just get there. Be safe. Number 4. Find the value of C that satisfies the mean value theorem for derivatives. Okay, so they're really specifying. Mean value theorem for derivatives with the function f of x is 1 over x minus 3 on the interval from 0 to 12. Now, what is the mean value theorem? Well, mean in this sense is somehow average. Well, okay, so what's going on? Well, it says there is some C. So this is what we're trying to find. F prime of C, which is equal to the average rate of change. So in other words, f of b minus f of a over b minus a. That's the mean value theorem. So average rate of change, the instantaneous rate of change. Well, okay, no worries. Now, what do we have? We have a and b are 4 and 12. We have our function. So we should make some notes. We need f prime of x. That's 1 over x, I'm getting ahead of myself, x minus 3 squared with a minus. Now, I did that in my head. Let's do that not in the head. So f of x really could be written as x minus 3 to the minus 1. And now bring that minus 1 down. That's minus 1. X minus 3 to the minus 2. And then chain rule says multiply by 1. And now you see that's where the minus came from. X minus 3 squared. So what do we have? We have a minus 1 over c minus 3 quantity squared. Okay, that's the f prime of c. Is equal to, well, now we have to do f of b. So that's, here we have this is our ab. So f of b would be 1 over 12 minus 3. Subtract f of a, 1 over 4 minus 3. And then we're going to divide by b minus a, 12 minus 4. Okay, well, let's work on it. Now, what can we do here? Well, 12 minus 3, that's another way to say 1 over 9. And then we have 4 minus 3. That's another way to say 1. So 1 over 9 minus 1 over 1. And then we have an 8. Well, okay. 1 is another way to say 9/9. And so we say, okay, 1/9, subtract 9/9. That's negative 8 over 9. Divide by 8. Well, that's, the 8's cancel. That's negative 1/9. And we're like, whoa! We want minus 1 over c minus 3 squared, but we not minus 1 over 9. That's looking promising. In other words, that looks solvable. We like things that are solvable. We can cancel minuses. So we have 1 over c minus 3 quantity squared equals 1 over 9. Flip both sides. C minus 3 quantity squared equals 9. Take the square root. C minus 3 is plus or minus 3. And so that tells us that c is 3 plus or minus 3. Well, so we can either do 3 plus 3, which is 6, or 3 minus 3, which is 0. Well, but we want to have it be one of our options, so it must be the 3 plus 3, the 6. There we go. Now, there were some computations here that got a little bit because of fractions and whatnot. But remember, if it says mean value theorem for derivative, instantaneous rate of change equals average rate of change, and you just plug in. And then from there, it's just carefully work, follow it along, and you'll get your answer. All right. Well, we're doing well. Okay. Number 5. Find the integral of x over x squared plus 1. And we have a bunch of options here. Things like a half log x squared plus 1 plus c, log of x squared plus 1, 2 log x squared plus 1, arctangent of x. That's a good one. A half x squared arctangent of x. Okay, so which one is it? Now, there's a couple ways you can approach this. Now, one way is, when in doubt, say, look, you're trying to find the antiderivative. Here's a bunch of candidates. Take the derivative of each one of them individually. One of these has to give x over x squared plus 1 when you take the derivative. And if you find that, you win. So that's one approach. Let's see if we can't do something else. So here, I'm looking at this. I see x squared plus 1. And I like x squared plus 1 downstairs. If there's a 1 upstairs, I do think arctangent. And I'm like, oh, I see that arctangent. But it's not a 1 upstairs, it's x. The other thing I say is, okay, so arctangent's not right. At least not right now. So what can we do? Well, in the back of my mind, I'm always thinking, is there a good substitution? Is there a good substitution? Substitution is like our default thing for integration. So we should always be on the hunt. Substitution, substitution, substitution. That just keeps going and going. And look at this, what if we tried the denominator as our substitution? Let's see what that would say. That would say u equals x squared plus 1. And so then du would be 2x dx. And then we're like, what? X dx? That's pretty good. Now, using our sophisticated marker technology here, we can move that 2 across. So what does that tell us? Well, it tells us the following. It tells us that we can say, look, the x dx becomes a 1/2 du, and the x squared plus 1 becomes u. And so the 1/2 just comes out. That's just a constant. And so, okay, so but what's the integral of 1 over u? Log u. And all right, well, are we done? No, because you got to put back what u is. So 1/2 log x squared plus 1. So the answer is A. All right, now before we leave this one, I want to point out one of these options which is really tempting. I want to point out why it's really tempting, and just warn you not to be tempted. A lot of people will look at this and say, you know, I see an x and a 1 over x squared plus 1. All right, and I totally agree with that. And now it's like, well, I know how to integrate x. That's a half x squared. I know how to integrate 1 over x squared plus 1. That's arctangent x. So shouldn't the integral of x times 1 over x squared plus 1 be the 1 half x squared arctangent x? And the answer is no. Integration works great with addition, because at the end of the day, integration is addition. It's just a big thing of addition. It does not work with multiplication. Now, there are things that we can do. Spoiler alert. Next semester, it's gonna be lovely. But for now, don't do that. So you cannot just integrate them piece by piece when you're doing multiplication. All right, that doesn't work. Okay, number 6. Find the integral of 1 over x log x. And now this is a definite integral because we have bounds. The previous one didn't have bounds, so that's why you needed a plus c. So, what can we do? Well, kind of the same process. We don't quite recognize this, but we say, is it close to something we can do, or is there a good substitution to make? And I see a log x, and sort of when I see pieces, I start thinking, what's the derivative of the different pieces? What's the derivative of log x? 1 over x. I'm like, what? I see a log, and I also see the derivative of log. That's just sort of like two flashing signs saying, here's the substitution, here's the substitution. So we are not going to ignore these signs. We are going to go all in. We are pushing our chips onto the table. This is a substitution where we want to go with log. So let's do it. Pay attention to the signs. So we will put our pieces together. Du is 1 over x dx. And we say, aha, this becomes integral. We still have the log x was downstairs, so that's still downstairs. The 1 over x dx, well, we'll put that as a d. We'll put that there. Now, be careful. Gotta update the bounds. These bounds are x bounds. We don't want x bounds. We want u bounds. So how do we get to the u bounds? Well, we say we have a relationship between x and u. We have u equals log x. So if we put 2 in here, we get log of e to the 2. And there's a nice fact about log. Log of e to something is the something, because they're inverse functions. They undo each other. So when we put in the e squared, we'll end up with 2. When we put in the e to the 6, log e to the 6 is 6. And so what do we end up with? This becomes log u and evaluated to 6. Okay, because the integral of 1 over u is log u. So that's log of 6 minus log of 2. Now, another property of logs, in fact, there's a few of them. We'll go ahead and write some down. If you have addition, that becomes multiplication. And if you have subtraction, that becomes division. So you say, okay, so this is really what? Log of 6 over 2, and that's log 3. Now, why did I do that? Well, because I didn't see log 6 minus log 2. But log 3, that we could do something with. And so, beautiful answer, log 3. Okay, now, a couple of things to note. Now, there's some really tempting wrong answers here. One tempting wrong answer is to say, hey, log of a minus log of b, maybe that's log of a minus b. and that would give you log 4. No. That's wrong properties of logs. But there's a more subtle one. A lot of people might be tempted to guess 4. How did that happen? Well, remember we said update the bounds. If you didn't update the bounds, what would happen is you'd have e squared e to the 6, and it would become log of e to the 6, log of e squared, 6 minus 2, which is 4. So 4 is tempting because it's a mistake if you forgot to update your bounds. So be careful, right? They have really good tempting wrong answers. Oh, those tempters. Oh, that's okay. We're not going to fall for their cheap tricks. We're going to get them because we're going to be great. On to the workout. And now we actually do have to be a little bit more careful. We have to explain, have to include details. That's okay, we don't mind. All right, so compute the following limits. And we have 2 of them. We'll start with this first one. Limit as x goes to 0, x minus 1 squared minus cosine x over e to the x minus 1. Now, the first thing you should try with limits is plug it in. Plug it in, because if you get something out, you're done. And if you don't, you kind of have an idea of where you're going. Okay, so what's happening here? Well, this is going to go to, when you plug in 0, 0 minus 1 squared is 1. Cosine of 0 is 1, so 1 minus 1 upstairs. Downstairs, we have e to the 0, which is 1 minus 1. Well, that's 0 over 0, which means, right, more work. More work. That's what we need to do. Okay, so we know we need to do more work. But what's our more work? Well, it's in the right form. Fraction, 0 over 0. We talk to our good friend, Le Hôpital. Ah, Le Hôpital, mon ami. All right. So we mark equals Le Hôpital, limit x goes to 0. And by the way, during the exam, you probably shouldn't start going out loud. But you can think it. You can think it. Nobody can stop you from thinking. But, all right, I digress. So, now the nice thing about L'Hôpital, not a quotient rule. You take the derivative upstairs, so 2x minus 1, and derivative of cosine, negative sign. And so minus minus makes positive sign. And then derivative downstairs, e to the x. Now, the good news is, if you plug in 0 downstairs, you don't get 0. What does that mean? It means game over, man. Game over. We're done. So, we plug stuff in. Like I said, downstairs, e to the 0 is 1. Upstairs, we have 2 times 0 minus 1, so that's 2 times negative 1. And then plus sine of 0 is 0. So we end up with negative 2. And there we go. So not too bad. Now, a couple of things I want to point out. One, make sure you show that you know you're checking that it goes to 0 over 0. They'll look for that. Also, it's nice to indicate what you're doing. So I put Le Hôpital like an LH, or you could say apply Le Hôpital, or whatever it is. And make sure you don't do the quotient rule. All right. But, other than those 1 or 2 small things, no big surprises. No big surprises. All right. Part B. Well, we have the limit as t goes to infinity. And what's going on? Well, again, plug it in. Now, what does it mean to plug in infinity? Well, what happens for large values of t? Well, the inside, 2 over t goes to 0, so we go to 1, and the t goes to infinity. So it's going to 1 to the infinity, which equals, you guessed it, more work. More work. Now, problem. We're not ready for Le Hôpital, because Le Hôpital needs a fraction. This is not a fraction. And so we can't do Le Hôpital, but we have ways of making things into fractions. What's our ways? Well, let's call our answer L. And now we'll say, there's a really convenient way to bring exponents down. And that is to use the log, right? So log of something to the something, a to the b, that's b log a. So we can pull exponents down. All right, so what do we have? Log L, that becomes, we can put the log inside. T goes to infinity, log of what we're trying to take the limit of. And by design, now we're like, that comes down. But you know what? Not only are we going to take it down, we're really going to go down. We're going to go all the way down. We want to put it down, down, down. Now, how would it look? Initially, it will come down as a t. But I need a fraction, so that's not going to work. So I'm going to keep pushing it down. So if it comes down here, it'll become a 1 over t. Okay, so first down in front, and then down to make a fraction. So, rewriting. This is the limit as t goes to infinity, fraction of log 1 plus 2 over t, downstairs 1 over t. Now you might say, well, hold on. Why did he move the t downstairs? Why not the log? And the answer is because that would not make things simpler. Our goal is simplify. So put this thing downstairs. That's simple to take a derivative. 1 over log, not that simple to take a derivative. Okay, so that's why we did that. And now what's going on? Well, this goes to log of 1 over 0, which is 0 over 0, which equals more work. But wait, it's the right kind of more work. It's our time to shine. Ah, yes, le hôpital rides again. Ah, le hôpital, mon ami. Only you can help guide us through this puzzle. So this becomes equals by le hôpital, the limit as t goes to infinity. Derivative upstairs. Well, 1 over 1 plus 2 over t. Chain rule, don't forget chain rule. The derivative of 2 over t would be minus 2 over t squared. Right? The 2 is a constant, and then 1 over t is like t to the minus 1. The minus comes down, and then you have a t to the minus 2. Derivative of 1 over t minus 1 over t squared. And you'll notice here, nice things happen. And if you've lived a good, clean algebra life, nice things will happen. The t squareds cancel. The minuses cancel. And now, there's really beautiful things. What do you have? Well, you have the 2. And now, this, right, that's that 2. And then this part is 1. Right? Because 2 over t goes to 0. So our answer is 2. Except it's not. What? Oh, we were so close. Why is it not 2? What did we forget? Follow the work back. 2 is not our answer. 2 is the log of our answer. So how do we get our final answer? Well, now we say, look, our answer, to get rid of log, you use the exponential function. So it's e to the 2. So don't forget, if you take a log, don't forget to do an exponential at the end to fix it up. Okay, and that was our number 7. Our first workout problem done. Number 8. Find the indefinite integrals. Okay, 3x to the 4th over x squared plus x to the 5. Now looking at this, we have a plus downstairs. This plus is what I call a bad plus, in the sense that we can't break up over it very easily, so we have to find other things to do. Now, keep in mind that when they give us a problem, they don't always give it to us in the nicest way. So we say, okay, well, maybe this hasn't been given to us in a nice way. so we can rewrite it in a nice way. Notice everything has powers of x's. What's the lowest power of x? X squared, right? So we can say, well, let's start to rewrite. So I'm going to factor x squared out of the top. And that'll leave us with 3x squared. And downstairs, we'll factor an x squared out. And that will leave us with a 1 plus x cubed. And of course, the x squareds cancel. Ha-ha! Good. So now, as we say, look, we have a much simpler problem. Don't forget to write, by the way, your dx. They're very particular about good notation. And good notation is useful. You know, it's not just a polite thing. It's good to have good notation. Now, how do we integrate 3x squared over 1 plus x cubed? Oh, now that's a good question. What we can do here is we can say, look, if I have 3x squared over 1 plus x cubed, well, it's not arctangent, right? Because that doesn't work. But again, in the back of your head, you're always thinking substitution, substitution. In other words, do I see, if I take a derivative of a piece, do I see that derivative somewhere? The derivative of x cubed is 3x squared. And that's like, whoa, hold on, hold the phone. So that's suggesting, let's go for the whole bottom. So let's put u equal 1 plus x cubed. And what would du be? 3x squared dx. This part up here. And like, wow. So this becomes the integral of 1 over u du. And, oh my goodness. You know, looking at the test now, somebody who wrote this test really likes the logs. Because we've done that on a lot of problems. Okay, so we get log u. Don't forget plus c. If you're doing an indefinite integral, if you miss the plus c, you lose a point. We don't want to lose a point. We love our points. We love all our points. Got to get them all. We're not done. If we started with x, we have to end with x. So we undo our substitution and say, well, u is 1 plus x cubed. And following good practice, we'll put parentheses here. So log of 1 plus x cubed plus c. There we go. Part A, done. Part B. Well, we have 1 plus x cosine x over x. Now, notice here we have a plus. This plus is what I call a good plus. What makes it a good plus, it says, hey, pull it apart. Don't think of it as one big thing. Break it into 2 medium things, maybe even 2 small things. Well, so let's do that. Let's take advantage of our good plus sign. So this would become integral 1 over x plus x cosine x over x. And we're like, oh. Now the first one, my goodness, log again? That's okay. Second one, the x's cancel. Woohoo! Okay, so with just a little bit of gentle rewriting, just a lovely gentle nudge here, push here, and we get to this. And each piece is now straightforward. Integral 1 over x, log x. Integral of cosine. Well, that would be positive sine. Yeah, it's one of those things, I'll tell you, the integral of cosine in science, I'm always super hesitant because there's a plus or minus involved in one and not the other. And so if you're not paying attention, it's easy to forget. Just as it's easy to forget our plus c, but we're not going to forget it because we're going to get all our points. And now we're done with number 8. Oh my gosh, we're flying. We could probably do this test twice. But I say let's just do it once really well. Number 9. Find the area between the curves. F of x equals x minus 1, e to the x squared minus 2x, and g of x equals x squared minus x minus 1. The shaded region in the picture below. Okay, so here's our picture. Simplify your answer as much as possible. And, okay, Hint, the two curves intersect in exactly 2 points, both of which have integer values. Well, that'll make it easy. Now, normally, how do you solve intersections? Well, you would say set them equal. So when does x minus 1 e to the x squared minus 2x equal x squared minus x minus 1? Now, there's a technical term for this kind of equation. The technical term is hard. This is a hard equation, so we don't want to do that. But let's take a look. We have a picture. Let's stare at our picture and say, well, it looks like they intersect here. And we have a grid, so this is saying maybe that would be 0. So let's try x equals 0. Now what happens? Well, what's f of 0? If you plug it in, you get 0 minus 1 e to the 0. You get minus 1. And what's g of 0? Well, you get 0 minus 1. Okay, so that's minus 1. They match, and so that is an intersection point. Okay, so our first intersection point was 0. One more to go. And, well, we're told they intersect in 2 points, both of which have integer values, and we need to go positive. So let's try 1. Why not? Okay, let's try x equals 1. What are we going to see? X equals 1. When we plug in 1, well, what's f of 1? Well, 1 minus 1 is 0 times something. Well, that's 0. Hard to recover from that. And g of 1 is 1 minus 1 minus 1. Negative 1. They don't match. Okay, so that's not an intersection. Okay, well, that's okay. There's lots of numbers. There's infinitely many integers. Don't worry. I don't think we'll have to try infinitely many. And let's try x equals 2. Okay, what happens when we plug 2 in? Well, we get 2 minus 1 is 1. Now up here we get 4 minus 4, 0. So we'll get 1 times e to 0, which is 1. Now, how about g of 2? Well, okay, that's 4 minus 2 minus 1. That's 1. Another match. A match made in math. Okay, so that's at 2. So now we know where we intersect. We go from 0 to 2. But we also know something else. Even though we failed at x equals 1, what we now know is that the top curve is f of x and the bottom curve is g of x. And you might say, well, how did we know that? Well, we just looked at the values. At 1, the value for f was larger than the value for g. All right, now, this is good. This is going to get us a lot of the way to our answer. So, how do we get more of the way to the answer? Now that we know where we intersect, and we know which one's on top, then to find the area, well, the area between the curves is going to be the integral from 0 to 2, first intersection point to second intersection point. And, well, I'll put it this way. A to B, the top minus the bottom. Okay, so that becomes dx equals integral 0 to 2. That's where we intersect. And the top curve will be our x minus 1 e to the x squared minus 2x. Subtract our bottom curve, x squared minus x minus 1. I'll put a dx there. I ran out of space on the side. Okay, so that's the integral we have to do. What? Really? We have to do that? Yes, we do. Because remember, we're going to go and get all our points. And by the way, in case you're wondering, is this a Steve problem? Yes. This is my fault. I'm to blame for this one. I'm responsible. Isn't it lovely? That's what I meant. Isn't it lovely? So, here's the thing. As I look at these two problems, I look at this and say like, because they feel different. We have a polynomial piece and something that's just not really polynomial. But we can take advantage of the minus. So let's do that. Now the minus says what? Separate it into two parts. Because sometimes what will happen is one part you'll do one thing and the other part you'll do a different thing. So let's break this into two parts. So we have the integral 0 to 2 of x minus 1 e to the x squared minus 2x dx minus integral 0 to 2 x squared minus x minus 1 dx. All right. Good. Now, we have to do both. Doesn't matter which order we do them. Let's think about this one. It's not looking great, but there's a suggestion, a hint of something. Notice this x squared minus 2x is a function inside a function. What technique do we use if we see function in function? We will go and do substitution. So if you see function, substitution. There's a reason we keep saying it. It's a beautiful, beautiful technique. So let's do a substitution. Let's see if it will work. Not every substitution does, but it's always worth it to try. You know, if we don't know something, try something. If it works, beautiful. If it doesn't, try something else. But never give up. You can do it. Keep trying. You'll find something. Now, when we take the derivative of x squared minus 2x, we get 2x minus 2 dx. And then we're like, whoa, hold on. Hold the phone. That's 2 times x minus 1 dx. Beautiful. Okay, so again, using our fancy marker technology, we can move the 2 across. So this 2 is going to go across. And so a half du is x minus 1 dx. So this integral becomes, I'm going to push this up here, the integral of 1/2 e to the u du. Okay, I think we've got a shot. Now, before we integrate, don't forget, update the bounds. You should always update the bounds. So we plug in. These are our x bounds. We're going to go and get some u bounds. So when x equals 0, what is u? 0 minus 0 is 0. When x equals 2, 4 minus 4 is 0. Now, without integrating this, what's the answer and why? The bounds match, so what's the integral? 0. So we can make a note here. The bounds match. So that way people know we knew what we were doing. So we say that equals 0. So that's half. We're halfway done. Now the other half, we look at and say, well, hey, that's a nice half because it's just a polynomial. We don't have to do anything fancy or tricky. No tricks on this one. We're not doing that. Okay, so the integral of x squared, 1/3 x cubed. Integral of minus x, a half x squared. Integral of minus 1, minus x. And plug in from 0 to 2. And if you plug in 0, you get 0, 0, 0. Good. So we just plug in 2. So we're going to have minus 1/3 times 2 cubed. That's 8. Then minus 1/2 times 2 squared, 4. And minus 2. Okay, so 1/2 times 4 is another way of saying 2. And so we have a 2 and another 2, so that's 4. So we have minus 2, minus minus 2, minus minus 2. So this right here goes to our 4. Then we have minus 8/3, which is the last part. 4 is another way of saying 12/3. So 12/3 minus 8/3 gives us a grand total of 4/3. And remember, we were told, simplify your answer as much as possible. I don't think we can do simpler than 4/3. You might say, what about the 0? Well, 0 plus 4/3 is still 4/3. Whew. I can tell this one was a workout because we almost filled the whole page. But we got the answer. Good for us. Good for us. That brings us to our final problem. It feels like we'd only just begun. Number 10. Let f of t defined between -4 and 6 be shown in the graph. Okay, hello graph. The curved portion is a quarter circle of having radius 2 and center at 0, 3. Okay, so there's a piece of a circle. Define a new function, capital F of x is integral from 1 to x of f of t dt. And now we're going to do some things with capital F. Find f of 5. Well, now, this f of 5, I can come up here and that says, look, I'm going to put in 5 for x. So this is equal to the integral 1 to 5 of f of t dt. So here's our 1, and here's our 5. Now, what are we going to do? Well, we're going to very carefully say, look, if we're after this, it's really an area, because we can think of integrals as finding areas. So we have a piece here, and then, of course, we have another piece over here, down below. All right. Good. Good. Well, maybe. Now, you might say, why did you shade 2 different colors? Well, when I said area, I meant area. You see how I put those area quotes, like area? Because we have positive and negative contributions. So we just want to make sure we get the right amount. So you can do this all geometrically. So how do we do it geometrically? Well, let's just break it into some shapes. And I'm going to say, look, you have a triangle here matching with a triangle there. Now, what's going to happen with these two triangles? They're the same area, but they'll cancel their contributions out. And so you'll get a net contribution of 0 from those. All right, now here I'm going to think about, I have a triangle on top of a rectangle. And so I say, okay, well, I can see the rectangle. That has 1 by 2, so that's 2. The triangle, 1/2, base, 2, and height, 1, 2, 3, 4. 4. Okay, so that's that portion there. And don't forget, because who would ever forget during a test, right? We're focused, laser focused. We have this last little piece down here. And because it's below the axis, it's negative, but it's a little triangle. So 1/2, base is 1, height is 1. Okay, so if we put this all together, what do we have? Well, we have 2, and 1/2 times 2 is 1, and then times 4 makes 4. So we really have 2 plus 4, which is 6, minus 1/2. Well, 6 is also 12 halves, minus 1/2, which gives us 11 halves. Okay, so there's part A. Now, we're going to go do part B. So, part B. Well, find f of minus 3. So that's the integral 1 to minus 3 of f of t dt. Okay, so we're going to go 1 to minus 3. Okay, so now we have a different region. But notice something about the bounds. They're not in the right order. Order matters. Orientation matters. We care about these things. So we need to fix it. So how do we fix it? Well, let's put them in the right order. So minus, and now you flip the order. So we can say, look, find the area and then put a minus in. Okay, so what's our area? Well, let's break it up into a couple pieces. We'll put a rectangle here. We'll put a rectangle here. And then we have the quarter circle. Now, let's do these two rectangles. We have 1, 2, 3, 4 is the base. 1, 2, 3 is the height. So we have negative 3 times 4, height, width, plus 2 times 1. You can also just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And 12 plus 2 is indeed 14. And now the other part is we say, hey, we've got that quarter circle. Okay, so how do we do that? Well, we know the area of a circle. It's 1/4 of it. So 1/4 pi, and the radius is 2, r squared. So the 1/4 because it's just a quarter circle. And okay, so as we mentioned, this is 14, so we have minus 14, and then 1/4 times 4, those cancel. We have the pi, don't forget the minus distributes, so minus 14 minus pi. Last part, C. Let h of x equal f of g of x, where g of x is 8 minus 2x. So recall, because it's off the screen, I'm going to rewrite it. Fx is the integral 1 to x of f of t dt. So h of x, that's our integral from, right, because that's f of g of x. So wherever we see an x, we're going to put in g of x. 1 to 8 minus 2x, f of t dt. Now, we're going to apply a really important result because we're after h prime of 3. So to find h prime of 3, we're going to find h prime of x, which means we're taking a derivative of an integral. So how does one take a derivative of an integral? Well, the answer is fundamental theorem of calculus. So in general, if I was taking the derivative of just capital F of x, what would it be? Well, it would be little f of x, right? That's the basic fundamental theorem of calculus. And more generally, if you're taking the derivative of the integral 1 to g of x of f of t dt, well, the derivative of the outside, right, that's the capital F, is little f. So this becomes f of g of x, and then times the derivative of the inside, g prime of x. Okay, so there's our sort of fundamental theorem of calculus type result. So for us, we say, hey, this is the derivative of the outside, this integral 1 to x f of t, would just be f, but plug that function 8 minus 2x in, times the derivative of 8 minus 2x, which is minus 2. Now, that's generic. We want specific. So we say, okay, so h prime of 3 is f of 8 minus 6, 2 times negative 2. So we need to find out what's the value of the function at 2. So we come here and say, what's this number? What is f of 2? Well, it's 1, 2, 3. So we're going to have 3 times negative 2, which gives us our final answer of negative 6. Final part of our final problem of our third exam. Wow. Whew, what a journey, what a journey. Thanks for joining me on this. I hope this helps, and I hope you're doing well. I know sometimes these ideas they take time to get used to, and I appreciate you doing the work. It will pay off. Believe in yourself. You're worth it. You're worth investing in. We believe in you. Good luck. We hope you do well, and we'll see you again on the other side. All right, bye.